this video, I want to talk about a way to minimize the number of nodes that you explore in a minimax game tree search, commonly called alpha-beta pruning. So alpha-beta pruning was first invented by two different researchers, this individual, John McCarthy, and also Alan Turing. They are both credited as inventing it independently. John McCarthy did it a little bit later on, but Alan Turing had never published it, and it was found in his notes after his death. And so both are credited of having independently discovered it, but John McCarthy is the individual who is quite famous actually for doing a lot of early game AI, and so he was the one who published the work on alpha-beta pruning. Now, what alpha-beta pruning attempts to do is it only wants to investigate branches that have a potential to change the optimum strategy that you're currently calculating in your search. What that means is we're going to try and keep track of how good of moves we've maybe already detected, and if we find ones that are too bad for either player along the way, we will just say, well, we're not going to explore those ones. We're looking for optimal play, and we use what we've explored already to help inform us as to whether a move should be considered or is too bad and should be pruned. To do this, alpha-beta pruning is going to keep track of two values commonly called alpha and beta, where it gets its name from, that are going to represent the best moves that we've found so far for max and for min. So alpha for max and beta for min. And we're going to start out, since these are meant to represent the best moves found so far, when we initialize, the best move, we're going to assume the best move so far is the worst outcome for each player. Sometimes we might initialize these values to, for instance, minus infinity for alpha, since alpha represents the best move for the maximizing player, negative infinity is the worst for a maximum, and then vice versa. We could maybe use infinity for the minimum player. It's also common if you know what the utility function looks like. So in a lot of the example games that we've been looking at, I've just been using +1 and -1 for win and loss, or for the maximizing player, and vice versa for the minimizing player, and then a 0 for a draw. This is very common, and so we might, if we know what that worst outcome is, -1 or +1, whatever it might be, we might use those values instead of minus infinity or plus infinity, because that actually is going to help the alpha-beta pruning algorithm prune maybe a couple extra branches. Because if after an update we find that a particular outcome we've discovered is equal to one of our alpha and beta, depending on some other criteria, we might end up pruning. And so having a case where it would be equal would be advantageous for us. So we initialize to the worst possible outcome, and then we apply the normal minimax algorithm, meaning we're going to start at the root, or we're going to start at the current state, or whether that's the initial state or the current state, and then we're going to recursively traverse the game tree in a depth first search manner. And as we do, we're going to pass the alpha and beta values down to our children as we go. Now, the updates to alpha and beta occur as we update the values of particular nodes in that traversal, meaning as we get information up from the nodes beneath us, if we're a maximizing node, we're going to maximize over them. If we're a minimizing node, we're going to minimize over them. Well, in this phase, if we find a better move, say we're maximizing and we've now find a better move than was currently recorded in alpha, then we're going to update alpha, and then vice versa for beta. If we are in a minimizing node and we find a new value that's better for beta, or it's better than beta for min, then we'll update our beta at this stage. Now, at this stage, what that means is at any particular node, we're only going to be updating one or the other of the two values of alpha and beta, depending on if we're in a max or a min node. But then after we do that update, usually what we do, well, especially if there is an update, if there's no update, we just usually move on, there's nothing to check. But if we have made an update and we've changed our alpha and our beta, then we're going to check to see how they're related to one another. If alpha is greater than or equal to beta, now remember alpha is meant to be the maximizer and beta is the minimizer, then this is going to be a branch that our opponent is unlikely going to let us explore. And so we can prune this branch and the remaining children of this node and return its value up to its parent node. So this can be a little bit abstract unless we have an example. So I'm going to now try and take us through a simple example. Now this is just a made up game for the purposes of exploring alpha beta pruning. But what we can see from this game, it looks like there's 3 moves in this game. First the maximizer moves, then the minimizer moves, and then the maximizer moves. Maybe this could represent, I don't know, a state in tic-tac-toe or something like that. And then after we follow these 3 moves, it looks like we arrive in a final state. No matter what sequence of 3 moves we make, after 3 moves we're going to end up in a final state. So what we're going to do is just try to apply the minimax algorithm to this structure, but also employing alpha beta pruning as we go. So to do this, I've created an extra little place where we can record the current values of alpha and beta. So I've used alpha for the up arrow because it represents the best move so far for the maximizing agent, and then the down arrow will be the best move for beta, the best move so far for the minimizing agent. And notice how I've initialized them. I'm saying the best move for my alpha or for my maximizer is -1, which is to lose. And then vice versa, for the minimizer, the best move for them is +1, which is for them to lose. So that's our initialization stage where we've initialized them to the worst outcome for each of our agents. Now remember, what we're looking for is to see if those values swap order. So right now, the alpha is less than the beta. If we ever get to a point where they're equal or alpha is greater than beta, that's our signal to start pruning. So we're going to move down. We're just going to do our normal depth first search. So we're going to traverse down the left-hand side. As we do, we're going to pass down our alpha and beta values down to the nodes as we go. Technically, we might pass it to this terminal node, but the terminal nodes have no use for alpha and beta, so I'm not depicting that here. And at this point, again, nothing has changed in alpha and beta because we don't do any changes until we start getting updates back from our recursion. So on the way down, we just pass it, and on the way up, we start doing checks. We do updates and checks. So the next step is for us to update this node's value and say, okay, so far, just exploring this branch, the best option for a maximizer is -1. At this stage, we're also going to compare it to the alpha value there and say, if this is better than our current best found move, then we'll update it. Well, at this point, we had -1, they're the same, so there's nothing to update. So we'll move to the next branch. The next branch, we find a draw, a 0. So again, we'll update the state here. 0 is bigger than -1. We're in the maximizing node, so we take the 0. And then we also update our alpha here, seeing, oh, this is a better choice than we had before. Now at this point, we might check, is alpha bigger than beta? Well, 0 is still less than 1, so no, we're not pruning yet. And one thing that's true about alpha beta pruning is usually along these first branches, we're unlikely to be doing pruning because we've just got our initial values in for our alpha and beta. It takes us a while to find good branches before we might prune some other branches. But at the moment, we found, a better move for our maximizer here. Let's go to our last node here. Our last node, oh, that's a -1. That means no update here. And so at this point, our maximizing node is done and it can return back. And it will return back, passing up its 0 up to this minimizer node. So now this minimizer, it's gone ahead and decided the best option for it so far is to make this move on the left, which will end up in a draw for it. And that was better than losing, is what it had recorded before. So we're going to update our beta in this node. Now at this point, again, we'll do a check. Is -1 greater than 0? No, it's not. So no pruning yet, at least not on this node. So the next thing we'll do is we'll try and traverse down its next branch. When we do, we ensure that we're going to pass down the alpha and beta values, the new ones. So there's a new beta value. This one got passed down a -1 and a 1. We got passed down a -1 and a 0 at this stage. So again, at this stage, we'll traverse down. We'll explore this node. It's a -1. We'll update here. No update to our alpha. And then we'll explore the next node. We will notice it's a 1. We will update our maximizing node to be a 1. And we will update our alpha to be a 1. And now we see that 1 is greater than 0. This is the signal for pruning. And what that means is this node now is done. It can just return back up its current value, which is 1. And that means we're going to prune off this last branch. We don't have to explore it. We've already found a good move. So let's try and explore why are we feeling like we can do this? Well, one thing is we've noticed that this branch here has found a winning state, which is this isn't why we've pruned, but this is something that sometimes happens when we're doing this, is we've found a winning state and we say this is the best move for this agent. We don't need to explore any other moves. But what's really happened here is we've compared it to the 0. What we're seeing is up above us on a layer above, we know there's a minimizer that's trying to pick moves of which move it should take, and we have to assume that it's going to pick optimally. It's already found a draw over here, so is it going to pick this move that's going to allow us to win? No, it's never going to allow us to pick this one. So this is a signal to us that this is a branch we shouldn't explore any further. Sure, it seems like it's a good branch for the maximizer, who is the current player, but we need to assume that the optimal minimizer player is never going to allow us to take this branch. So that's why we're going to end up pruning. So in this case, we pruned off this branch and we can move back up. At this point, we actually returned back a 1 to this. And as I sort of was mentioning already, the minimizer is not going to update its value. It's trying to minimize. So it's going to pick the 0 branch and keep the 0 branch. So no change to its value, no change to its beta value either. Then we're going to recurse back down onto our last branch here, passing down the values that we currently have, -1 and 0, same as before. And let's just explore this branch. So we see a -1. We're going to update here. No update to our alpha. Exploring the next branch, we get a 1, and we get the same instance as before. Seeing a 1, we now see, oh, this is not an advantageous branch for the minimizer. So the minimizer is not going to select it, so we can prune off any remaining siblings of that terminal state, and we can return ourselves back up. At this point, the minimizer is done, and it's selected its value of 0, so it can now return that 0 back up to our root node here, which is a maximizer node, now saying that the best that this maximizer has found so far is that it can have a draw. So we can continue along. We're going to now recurse down into this next option for the maximizer, passing in our new alpha and beta, okay? So when we updated the 0 here, we updated our alpha from -1 to 0. So now we can pass that in. That's allowing us to take into consideration the best move that we found all the way up on the top level now as well. So coming all the way into this node here, passing our 0, 1 for alpha and beta down, we find ourselves with a -1, and we update our value. -1 is not better than the 0 we already had coming in, so we're going to not update our alpha in this case. Now you'll notice I put all -1s here, so after we do 2 more updates, nothing has changed. It's still a -1 on our maximizer. So if the minimizer can pick this move, then the maximizer is forced into a losing situation, which the maximizer does not like. So we'll see how this is applied now. When we pass that -1 back up to our minimizer, this is the minimizer saying, oh, this is great, I'd love to be in this state, okay. But now what we do is we've updated the minimizer, we've updated beta from its 1 to -1 now, saying the best move that we found for the minimizer in this particular subtree is the minimizer can win. That's awesome. But outside in the subtree we've already explored, the maximizer up above us has already found a draw. Is the maximizer going to play this move that forces itself into a force move? No. Or forced loss? No, it's not going to do that. So for the same reason as we were pruning these simple branches before over here, we can say this node is so bad for the maximizer that we don't need to explore the other branches. They could also be losses. They could be all wins. They could be perfect wins for the maximizer, but it doesn't matter because the minimizer would force us into this loss and we don't want to go that direction. So we're not going to pick this option. So that's what the pruning is saying. This is a bad move. We're going to cut them off. We're going to continue exploring. So again, for the maximizer, we found a draw. The draw is better than this branch, which would be a loss automatically. And since we found that it might be a loss automatically, we prune off the rest of its children. All right, let's explore the last branch now. Again, passing in our same, it happens to be the same values now as we did in our last branch because nothing was changed in our maximizer when we pruned. So we're going to go ahead and go down this branch, and this time we find a 0, so we'll update our value. Well, that's the same value we had there, so that's fine. Again, checking our 0 and 1, we're not doing any pruning. We find a -1. -1 is not better than 0, so no changes. And then we find a 1 that is better, and notice now 1 is equal to 1. This is actually a signal for us to prune. Unfortunately, there's nothing for us to prune. There's no other siblings for us to prune in this particular node. So we can go up and look at our next node and see how that would be different if our nodes were explored in a different order. This is an important thing in alpha beta pruning, is if you explored your nodes in a different order. So our next one is going to be very similar, but the first node that we're going to find is a 1. When we see it's a 1, aha, now we can prune those other two nodes. So for this reason, it is sometimes common in alpha beta pruning to have a very strategic way about which you order the actions that you investigate. You want to investigate what are sometimes called killer moves or killer actions, things that are going to do something, big, instead of the silly moves that a human would already consider. Why are you moving your pieces backwards or something like that? You should start with the ones that are more aggressive and are likely to be winning moves. Okay, so that happened here, and we can see that will happen again in this next one. Well, if the 1 came in the middle, we only get to prune off one particular branch in that case. So we've gone through a pretty good example here of how alpha beta pruning works with just a simple toy game. But I want to just show you how this works again in a simple example with tic-tac-toe. And I'm actually not using numbers at this point. I'm just going to use some colors. I'm going to have alpha and beta here. Alpha is going to be updated here to be blue. The blue player, the O player loses, so blue is going to be the color for O. And then red will be the color for X. So I've just got them initialized to, you can think of this as -1 and +1 at the moment. Now we're going to explore. I've also started us off not at the initial state because that game tree is really big. Luckily, with alpha beta pruning, you can prune a lot of it, especially if you select your moves in a strategic way. But I've picked an interior state or a possible state you might arrive at after playing a few moves of the game, just to minimize the size of the tree a little bit to make it a little easier to explore. So moving down, first thing we'll do is explore one arbitrary game. So I've just placed an X in the first location that I might make an X, and an O in the first location that I might place an O, and the X in the first location that I might place an X. And I've just passed my alpha beta down as I go. Now this is a draw, so I'm going to signify that with a gray. And as we move up to the next level here, we update. This is a maximizer node because the choice is to pick which move for X. And so it's going to update its alpha. Gray and red, that's so again, if we're turning this into numbers, gray is 0 and red is 1. So this is not a mismatch, so no pruning at this point. So we'll return up to the next node as well. It's going to be a gray as well, and in this case, this is a minimizer node, so we'll update our beta. And it's got a draw as well. The best move to minimize in this node is to get a draw. So we'll explore our next node. Our next node, place an O here, place an X here. This is actually going to be a win for our X. And when we bring that back up, we're now going to have our alpha updated to a win. This is a case that says alpha is a win, that's a 1. beta is a draw, that's a 0, 1's bigger than 0, this would be a case where we would prune some more branches, but there are no other branches. So if we had actually explored these two in the opposite order, we would have pruned one of these branches. Now we're done this particular minimizer node, so we pass back up to the maximizer, our original state. That's saying the best thing we found so far is a draw. If we go to the left and our opponent plays optimally, we end up in a draw. Even though there's a chance for us to win here, that's only if our opponent does not play optimally. So let's try our next option. Our next option is going to place our X in the bottom left. This is an immediate win for us as the maximizer or as the X player. And when we return back up and we update this value, we now see that we've updated our best possibility to be a win, and this is a signal for us to stop to prune. We don't need to explore the final branch. There's another branch over here. We don't need to explore it because we've already found a winning move. And this kind of coincides with the kind of reasoning that a human would do. Okay, a human in this situation might try and look at the different possibilities, and when they find the winning move, they usually don't explore any other possibilities because they're employing a kind of alpha beta pruning in their own mind. Okay, so again, alpha beta pruning is going to be a technique that is going to allow us to prune certain branches in a minimax tree. Why is this going to be advantageous for us? Well, remember, these trees can be really large. And because they're really large, we're going to only explore them down to a certain depth. And we want to get as deep as we can. Well, if we can prune off branches that are not going to be advantageous to us, then we can probably get deeper. And if we can get deeper, we can think better about our moves, and hopefully we can come up with a better move. So that's our presentation of alpha beta pruning. Thanks a lot for watching, and we'll see you in the next video.